Great. So our next speaker is Ken Brown from Duke University, and he's going to tell us about compass codes, theory and practice.
All right. It's great to be part of this workshop. The talks have been really phenomenal. I'm, of course, a little bit sad that we can all get together in Banasque. For me, like the challenge of this stay-at-home period is that you see all these things that remind you of error correction, and you can only talk to people via email. So, of course, the tile in my house, like everyone's house, is some sort of color code. And so after taking a shower and thinking about that, I go downstairs to get breakfast. And breakfast, in some sense, is a little bit better. Shouldn't be any sort of error correction triggers in breakfast. But it's not really the case, right? So I take out my vegan bacon out of the oven, and I think maybe it looks like some sort of vegan Bacon-Shor code. I put a little bit of fruit on my waffles, and then I basically start trying to do some kind of matching algorithm. Can I figure out the errors that have caused these blueberries or the errors that have caused these bananas to appear? And then I realize that I have basically a code with only smooth boundaries, and so there's really nothing to do anyway. So what I really miss about meeting in person, though, for conferences is not just the beautiful mountains that are in Banasque, in this case in Aspen, but the just kind of random things that people say to you when you're getting coffee or you're on a break. So at one conference in Aspen, Cody Jones said to me, "Oh, the rotated surface code is just a gauge fixing of the Bacon-Shor code." And I knew enough about the Bacon-Shor code and the surface code that as soon as he said it, it was immediately clear to me to be correct and true and interesting. And I was surprised I'd not thought about it before, but I just had not thought about it. And I feel like that's the beautiful thing about in-person conferences is these like just a tiny sentence here and there, like gets your mind thinking about things. So what I really like about this connection is if I think about spin models, if I think about the Ising model, like a ferromagnetic Ising model, that directly maps to the repetition code, right? There's a one-to-one map there. And then when I think about a compass model where I have spin interactions that are both Z-type and X-type, but still Ising-type interactions along the two edges, it does not directly map to a code, right? There are too many, there are basically too many checks for the number of degrees of freedom we need. And so then we have to build up these compass codes. So when I think about it, what I'm trying to do is I'm trying to take pairs of these bonds, multiple sets of these bonds, and put them together in order to make some kind of stabilizer code. And so what's nice is, Shor's code, we can think of, this is of course not how Shor derived Shor's code. Shor derived it from concatenated repetition codes. But we can really think of it as basically taking these blue type bonds, putting all three of them together to form these large weight 6 stabilizer checks. This, of course, naturally then follows for Bacon-Shor, where we just make sure that everything's symmetrized. And we have a subsystem code where the extra degrees of freedom, there's a few extra gauges which are left to float around. And of course, the rotated surface code also directly follows where we just pick make just a different choice of how these different gauges go together to form stabilizers. Now, Bacon-Shor code, of course, on the one hand, I think is not very popular because there's no threshold with increasing L. You can show that the probability of an error on each qubit has to drop like 1 over L in order for the code to help you out. And what it means is that for any given small error probability, there's actually an optimal size. So you would just grow the code out to the optimal size and then you would stop. On the other hand, if you want to do concatenation, concatenating with distance 3 Bacon-Shor codes has one of the highest concatenated thresholds of all concatenated codes. And you can also make slightly extended codes following the work of Yoder, which enables you to do something which is almost a transversal CCZ. It has a little bit of extra, a few extra tricks there. And now the surface code, of course, everyone knows and loves. It has a great threshold, it has local checks, and as we learned yesterday, it can be incredibly good for bias noise if we just change a little bit kind of the local direction at each qubit. Now, what will be interesting is I wonder, like, on the Bacon-Shor side, of course, there's probably tens of papers. On the surface code side, I'm sure there are hundreds of papers. And of course, the surface code is very challenging to outperform because of all of the interest that people have put into studying it. But when Cody mentioned this thing to me about the connection is different compass codes, I just began to wonder, like, at what point does this threshold arise? Like, how can I go from Bacon-Shor to surface code, and where does the threshold arise? And so I had the following cartoon picture. I imagine there is just a sea of bacon. And the problem with the bacon sea is that the errors can just easily sail across. They happily sail across from one side to the other, looting one side, bringing back their treasure, I suppose. And what I was curious about was, well, what happens if I start to put in islands of surface code that have popped up into this bacon sea? How big do these islands have to be? How many islands do I need to effectively stop these pirates and generate a threshold? Yeah, so I was, kind of mulling about that. And so then working with Huyan Lee, Daniel Miller, Yukai Wu, and Mike Newman, we were able to actually answer that question by looking at a whole extra set of codes that come from basically different fixes from the compass model. So one nice thing, which Mike Newman's idea was to take this idea of my loose idea of islands and think about it in terms of randomized codes. So on the left, we have a randomized code which goes from Bacon-Shor to the surface code by basically determining whether or not the squares that are going to become the surface code are broken into these different gauges. And we're just looking at just the one-sided error of trying to fix, say, for example, X errors. And what you see is that as soon as you have basically a linear amount of surface code density, the critical probability of the threshold basically grows linearly with the density of these codes. So that was quite nice. And then similarly, we could look at the other kind of limit, which is, let's start at basically the Shor code, which is really bad at X errors. So you have giant weight 2LZ stabilizers, and we know there's no threshold at 0. On the other end, you actually have L copies of the repetition code. So we know the threshold is 50%. And we see this sort of quadratic gain as we basically cut these giant 2L stabilizers into smaller pieces. And so that's quite nice. Answered the question that I had, which is, what do we do with these islands? The other thing that you can think about, which I think is very similar to some work done on kind of what's the optimal surface code given errors that are not homogeneous in space, we can do the same thing. So places where we have more of these, in this talk, these red checks are always Z-type. These Z-type checks, we can have more like weight 2 Z-type checks in a place where we expect more X errors. And we can have more X-type weight 2 checks in a place where we expect more Z errors. And so if your quantum computer, it has both an anisotropy in errors, but also that depends on the actual physical layout, which seems highly likely, it's possible to massage the compass code a little bit to give you better performance. Now, for example, let's just assume that it's a homogeneous bias, and we're looking at this ratio of, say, PZ over PX plus PY. What you can do is you basically, this is the one that corrects for X in my notation. So there's an abundance of X. You basically increase these Z-type checks that are a little bit longer. So instead of being 2 by 2, they're now 2 by 3. And that generates more X-type checks, which then corrects for more Z-type errors because it's going to see more. And what we found in the code capacity model is that as the basically as this bias increases, we're able to increase these lengths and to get better overall threshold performance. And that this follows to the phenomenological model and actually gives phenomenological thresholds, similar to the work in Tuckett, where we think about shifting surface codes to be, say, X and Y type to look for Z type errors. And these threshold values, we calculate using this union-defined decoder. So those of you who've heard me talk before know that I'm really interested in circuit level model. Like I want to make codes that correct bias errors when I actually have gates that I have to account for. And what's nice about these extended codes is that we're able to still use a single syndrome qubit to do these checks, even though these checks are now weight 6. So there was kind of hints of this from the rotated surface code Tomitas Fourier paper. We showed it for the 9-qubit Bacon-Shor code. We then showed that it should work for all compass codes, but didn't have an algorithm. And in this last work, we actually showed the algorithm and explained how to make the decoding graph. So basically, we know what the correlated errors will be, and then we fix it when we look at our other decoding graph. So then, my student Shilin developed a weighted union-defined decoder, which improves on the performance of the union-defined decoder, and then looked at whether the bias, if I have bias in the memory, but basically depolarizing errors in gates, how does that depend on both the size of the surface code, which here n is the length, 7, 9, and 11, and then this elongation, which should help with the bias. Here we have infinite bias. And what you see is that due to the depolarizing gate errors, the elongated codes do help with the bias, but as the codes get larger and larger, the ratio of that gain goes down. So you need to really take advantage of the circuit level model. You need some of the techniques that Shruti talked about with gates that actually preserve the nose bias. I also want to point out that we use the weighted union-defined decoder to look at the surface code using a standard error model. And you see that it takes the unweighted union-defined threshold from 0.38% to 0.62% using the full weights. And we find that if we actually just truncate it to have like a finite set of weights, we get almost the same quality threshold, and the decoder is really quite fast. Okay, so now that we have this set up, what can we do theory-wise? Excuse me. All right. I'm always interested in this question about coherent errors. So if I have a polyphase noise and a coherent error that has the same fidelity, they have quite different action, right? The coherent error preserves the Bloch sphere, the phase slip error shrinks the Bloch sphere. And this is a process matrix representation in the limit of small theta. Now, what people usually worry about is coherent addition. So if I put two of these rotations together, I get quadratically worse fidelity. If I put two of these depolarizing channels together, it just adds. If I look at the diamond norm of these two channels, the two diamond norms just add, so that seems fine, although this diamond norm is much worse. Now, of course, coherent errors are in some sense not a problem, because if you are guaranteed they're perfectly coherent, you can perfectly cancel them. And so whether or not they're, whether or not they're worse or better is kind of a little bit of a matter of perspective. So what's interesting is we know that measurement of stabilizers also decoheres errors. And so what happens when we look at these really large codes? And so, for really large surface code, there's this nice tensor network paper by Darwan and Poulin, and then this Majorana representation by Bravi, Engelbrecht, Koenig, and Perd. And what you see is that as the as the size of the surface code gets larger, you basically limit to very small angle rotations and basically no error. And then this little peak at pi/2 is actually due to the decoder not being perfect, which is intriguing. So around this time, myself and Stephanie Bill, Joel Wallman, Mauricio Gutierrez, and Ray LaFlamme, and Juan Doherty and Flammia basically came to the same conclusion, which is that as the distance of the code grows, these coherent errors basically go away, where it has to do with kind of the underlying fidelity becoming smaller. And these papers, we take different approaches. We basically get to the same result. So this is fine, and everything is good. But then there's this paper this year by Iverson and Preskill, which tries to calculate what it is for the surface code. And they come to the conclusion that the critical angle that you have to get to has to be smaller than 1 over the length of the code. And I had thought that the authors back on this page had shown that we just needed to be below threshold. But then when I looked again at these papers, of one of which I was an author, I saw that we indeed below threshold, but we just say far below threshold. There's actually 0 bound, just that it has to be small. So this 1 over L bound is like a real improvement. But if you look at the numerics from the Bravi paper, it looks like it should be constant. And we know for the repetition code that it's basically pi/2. So what's interesting is maybe we can use compass codes to try to solve this problem.
Sorry, but Ken, isn't that potentially an artifact of the proof in the Iverson and Preskill paper?
Oh yeah, this bound is not strict for sure. This bound,
like they show that it's sufficient when that happens, but they don't show that it's necessary that you do that, right?
That's right. They show it's sufficient, but it's not necessary. So I would say here, you and I, Steve, show that if theta is really small, it works. But we actually have no limit on small. And then what they show is that, oh, theta less than 1 over L is sufficient, but as you said, not necessary, right? And we know numerically it should be, it looks like it's less than some constant.
Yeah, so and for the hashtag open problems section, I think there are a lot of open questions related to these types of error correction increases, stochasticity of logical noise. I don't think we understand that very well.
Yeah, that's right. That's right. So here's where I think compass codes actually can give us a little bit of a handle on trying to understand it. So if I look at this Shor surface plot, again, this is for stochastic errors. The 2 ends, on this end is the one which is the worst against Z-type errors and coherent Z-type errors. And this side is the best because it's just 3 repetition codes. Now what's nice is my student Dripto and I, we can actually calculate exactly the critical values for these 2 sides. And we see this side here is the 1 over L value of Iverson and Preskill. So we show that basically that, well, we suspect that that basically shows this has to be bigger than that. And then what we're working on, because I also think the nice thing about workshop is we've talked about kind of open things, is basically using a continuation of compass codes that walk from the Shor code towards the surface code and show that coherence angle increases. And it's yeah, and that's what we're up to. I'd love to talk to anybody about it. I actually think these are sort of my conjectures, which is that if you have an incoherent Z decoder that has a threshold, the coherence threshold can be related to that angle. And this is a worst case, which comes from the far bad Shor side. And then this second conjecture I have less faith in, but based on looking at the numerics from the Bravi paper, it actually looks like even if you're not doing maximum likelihood decoding, the maximum likelihood threshold is actually the place which is setting when the coherent errors are suppressed. Because that residual error you get from not having a perfect decoder, using poly corrections anyway, just really looks like an incoherent error. So those are two conjectures. They're not proven. We're working on it. Now, the other funny thing that happened, and maybe this is where the vegan bacon could come in and say, is that if you have coherent errors, the signs of the stabilizers matter. So if you just make it, instead of a ferromagnet, you make it an anti-ferromagnet, then this guy also rises up to pi over 2, because all of these errors basically cancel to be a single qubit. Now, one nice thing about Duke University, and when everyone can travel again, I hope everyone can, and please let me know if you'd like to come visit. We'd love to have guests. So Robert Calder-Dubank's group has been working a lot on condition, and particularly student Narayana Rangaswamy, on what are the conditions for whether or not Clifford hierarchy gates can happen on a code. And so we were talking with them, and they had just shown what the conditions were so that you could apply all of these, transversely apply all these rotations to pi to the 2L and preserve the code space. And one example code is just a Shor code with L even. And it turns out when L is even, because it's an anti-ferromagnet, this overall coherent error just vanishes because it's a decoherence-free subspace to that code. And it's intriguing to me because they did not come at it from that direction. They came at it from the direction of like, what are the constraints on classical codes that enables us to do transversal RZ rotations. Okay, so now for the last bit of the talk, a little bit about coherent codes in practice. So the smallest compass codes in practice, the smallest compass code is these simple quantum error detection codes, 412 code, 422 code. And then I have a plot from this paper we did in collaboration with the University of Maryland, where we basically showed that we could actually do prep and measurement at an error which was comparable to our physical qubit in a little bit better. You know, there have been excellent works on doing fault-tolerant gates. And then recently, from ETH Zurich, this work on showing multiple rounds of stabilizers doing the error detection from the group of Andreas Walrath. So that's good, and it's the first step. Now, you may have noticed that there are more papers lately which are about the nitty-gritty of actual errors in actual systems. You'll see a rise in discussion of things like crosstalk. You'll worry about things like, what is the timing of doing these things? And so in this paper, which from Marcus Mueller and others, they really go into the details of how to do the Steam code on a TRAP9 system. In this paper from Chamberlain and coworkers at IBM, they look at these heavy hexagonal codes, which are actually an example of compass codes. From our electronic masters of ceremony, Boris, there's these things about what do you do if you have different leakage rates in qubits in the superconducting system. And then from my own group, we have this recent paper where we actually make sort of like phase diagrams of, given like the real physical errors, what's sort of the best code to use. And all of these examples actually come from teams, independent teams who are working as part of this IARPA logic program, where the goal is to implement a logical qubit. So I just want to briefly tell you about this work we've been doing with our collaborators at Maryland, Chris Monroe, and you may have seen on Twitter today that he's moving to Duke, so we will all just collaborate down the hall soon. Where they do an amazing thing. So they have an experiment where they have 15 ions. This is the picture of the ion chain. You'll notice that these last two ions are spaced a little bit further away. So we don't use them as qubits. They basically serve as sort of like end electrodes, which keep the other ions closely spaced. We take advantage of the fact that the Bacon-Shor code, the 9-qubit code, has a really easy fault-tolerant preparation. Typically, in a quantum error correcting code, to do fault-tolerant prep, you need to do some gates, then you need to do some measurements to check things are working. Here, we can actually do the gates directly. So that's 9 ions. And then we have 4 additional ions for 13 total ions, which we use as the syndrome qubits to check these only 4 stabilizer generators we have. And then, of course, we're interested in things like logical operations. All right, so again, what's nice about Bacon-Shor is that because of this underlying repetition code, the Shor structure in a certain gauge, you really fault-tolerantly only need to generate 3 copies of this GHZ state. Now, you can do a non-fault-tolerant preparation where you first do some rotation to choose where you are, basically in XZ, in the XZ plane. And then you apply these 2 entangling gates so that you actually have a fully entangled system over all 9 qubits. So we experimentally, the group at Maryland has run the following experiment. They prepare the logical states. They measure in the appropriate basis of that state. So if we prepare in Z, we measure in Z, prepare in X, measure in X. And then we compare the ideal outcome to the measured outcome as a function of what we do. So in the raw case, we don't do anything. We just accept the parity we've measured. In the correction case, we use the stabilizers kind of classically at the measurement phase, right? We don't use measured stabilizers, we use the classical data to do a correction, which is important for fault-tolerant measurement. And then in the detection stage, we throw out anything that detects an error. And what you can clearly see here is, no surprise to anyone at this conference, is the huge gain of fault tolerance, right? That at the raw level, the errors are pretty comparable. Once you get to the corrected level, you see already that the fault-tolerant preparations are much better. And when you get to the detection level, it's pretty unbelievable. I would like to point out that to prepare plus and minus, we actually apply the fault-tolerant gate to 0 and 1. And that's why the errors are a little bit larger. That's basically the error from the fault-tolerant gate. And that actually, that the corrected spam error for preparing and measuring the 1 state is better in the logical qubit than it is in the physical qubit. Now, it's not the case for the 0 qubit, the 0 state, because in real life, the measurement errors are not symmetric. So I think it's really hard to beat the physical 0 error. Now, to look at gates, I need to remind you just a tiny bit about subsystem codes. So in subsystem codes, you have degrees of freedom, which you basically don't worry about, called gauges. And the way that a fault-tolerant pi/2 Y gate works for Bacon-Shor is that you actually, when you apply it and a permutation, you actually switch the gauges, which from a big perspective doesn't matter, but it is something to keep in mind. And if we do this non-fault tolerant prep I talked about, which is the red line, or we apply this weight 5 polyoperator direct operation of the logical Y rotation, we're able to, with this preparation and with this direct operation, we're actually able to generate all states in this in the XZ plane, and we actually stay in the same gauge, because the gauge is basically here fixed by preparation, and here this choice of logical Y operator doesn't change any gauges. So when we do that, what we do is we plot, because of being atomic physicists at heart, we plot some sort of Rabi oscillation. Now for the fault tolerant case, you can only go 0, pi over 2 pi, pi over 2 pi. For the non-fault tolerant prep and for the for the non-fault tolerant gate, you can of course go to any angle. And you see actually really, to me, like really phenomenal results once we're able to do the correction, both for the direct preparation and for the fault tolerant preparation. We get incredibly high contrast, meaning that the like the overall size of the block sphere is good. And then when we look at kind of how it's decreasing with the angles, the kind of surprising thing is that for the large continuous rotation, the gate is actually quite good. It's just that the constructing of the gate, the noise that it generates, which ends up looking kind of like a random noise, really drops the amplitude. So our fault tolerant gate error is about 0.3%. And then you can kind of estimate from going to pi over 4 that the encoded magic state prep error after correction, where it'll be limited by this, the amplitude here, is about 2%. And there's a star there because it's not a, it's, you know, again, it's about 2%. We've been able to.
Can I just ask, is that 2%? You estimated that number, or is that like interpolating from?
Well, yeah. Okay. So I have the, so imagine that this curve. So what does this curve not see, right? The curve doesn't see the face, so it can't tell if I'm doing a Z rotation, or I can't tell if I'm doing an X rotation or a Y rotation. But we have good reasons to believe we're doing a Y rotation, which I could go into. So if we accept that, then the error at pi over 4 is limited by either this, which is kind of the error per pi over 2 gate, or the contrast, which represents kind of, I mean, effectively kind of a depolarizing channel. And what we see is the contrast for the direct preparation is 98%. And the error per operation up to our statistics is 0. And the reason is that preparation is controlled by just one single rotation, which is quite good in the system. So, right, so there's that one single qubit rotation, which is really good. There are two kind of, these two entangling 2 qubit gates, which are less good, but they should both fail at about 1 or 2%. So you'd sort of, like, if you don't do any error correction, as you can see in the raw case, you know, it's below 80% based on measuring this parity. But if we're able to do correction, then it's clear that most of those errors are correctable single qubit errors. And that's where we get the 2%.
And you have, including questions, 6 more minutes. So.
Okay, good. I'm basically done. I just wanted to say that we tried to see if we could measure, we can measure the 4 stabilizer checks. So in this experiment, we measure the 4 stabilizers, we measure the 4 ancilla, we measure all 9 data, and we check to see if the ancillas have detected introduced errors. And what's great is we can see the introduced errors. The downside right now is that the gate fidelity is not quite high enough for that to help us. So it's better for us just to run whatever gate sequence we want and then measure and correct on the measurement than it is for us at the moment to do these stabilizer checks and then correct. So yeah, so in conclusion, I think what's nice about these compass codes is it gives you like a family of codes with fixed code parameters. I think it's really phenomenal that experiments are entering this area of fault-tolerant quantum error correction. And I do think that we need more refinement of fault-tolerant procedures for the physical errors that we actually have. And I think that's a common theme in this workshop. I really want to thank Chris's group here whose experimental results I showed. They've been really doing an amazing job in this time of COVID and have been able to run basically all of those experiments remotely. And I'm very happy that they and Chris will be moving to Duke shortly. And then on my team, again, I really appreciate Mike Newman helping me formalize this idea of C's of surface codes, Muyan Lee for all this work on Bacon-Shor, Dripto, who's been working on this coherent part, Shilin, who's invented this weighted union find decoder, Narayanan, who's Robert's student, who's been doing a lot of work on code spaces. I didn't talk any at all about Natalie's work, but hopefully you saw our QEC19 talk. And then my undergraduate, Catherine, has started an undergrad quantum society. And I'm very thankful for all of the funding agencies and for this work, particularly IARPA. And with that, I'm happy to take 5 minutes of questions.
Thanks, Ken, for a wonderful talk. And yeah, your Bacon-C animation is fantastic. I was really hoping Dave would be on the call so that he could see that he has the Bacon-C named after him now. There's only 2 scientists that have a C as far as I know, Fermi and Bacon. So are there I Ken? I see one. Hold on. Okay, actually, that looks like it's for Naomi. Sorry, Ken.
Fine, that's fine.
Does anyone have questions for Ken?
There's actually somebody raising their hand. So
can we?
Yeah.
We can probably unmute him.
Yes. Hi. Thanks, Ken, for the nice talk. It's nice to see the progress. Can you go back to the slide with the state preparation where you have these different gauges? Yeah, this one.
Yeah.
It reminds me a lot about these coverings in mathematics, right? Where you have, like, for instance, the real line is the covering of the circle. You know what I mean?
Yes.
So this looks like 2. I mean, of course it is, but it looks like these 2 sheets, which are a copy of the. I mean, do you know?
Let me just say one thing, which is kind of interesting to me, is that there are many along these ideas of sheets and coverings. So here, where we apply the logical Y, directly apply the logical Y rotation, it is really critical that that actually preserves your gauge. If that doesn't preserve your gauge, you'll end up with an entanglement between your logical data and your gauges, which that is like very disastrous. So there's sort of some limits on what you can do in this space of gauges. But there are many, many, many possible gauges. Well, I mean, for 9-qubit code, not so many, but generically.
So is there some work about gauge or subsystem codes and these sheets and coverings?
I think, oops, sorry. I think the closest thing that I know of, if I could jump in, and Daniel Gottesman is on the call, is trying to understand fault tolerance using the language of fiber bundles more formally. I'm not sure if that is at all related to this idea. Maybe you're talking about Riemann surfaces.
It is. I know what you're referring to, the one with his wife.
Yeah, Daniel has something to add to that.
I think it's not related to subsystem codes.
Not very much. I mean, it's you know, the continuous paths allow you to define a path in the Grassmannian. So there's a little bit of connection there. It's not obvious that there's anything more than that. But that's maybe the right frame to start to think about that connection.
Good pun with the word connection, Daniel.
Yeah, well,
I think we're out of time for questions. If you have more questions for Ken, ask them in the Q&A or in the Slack. Ken's going to upload his slides to the Slack channel as well. And let's thank Ken for a wonderful talk.